Hi, today we'll start on chapter 7, and chapter 7 is about work and energy. Work and energy. Now, if you remember so far what we did, we talked about motion in one dimension, chapter 2. And then after that, we talked about object moving in 3 dimensions. And we used the equations of motion. Then after that, we looked at the cause of motion, and we talked about Newton's law, F net equal ma, Newton's second law, the cause of motion. Up to now, what we did is that we used forces. And remember, when you deal with forces, it's not that easy because they are vectors. You have to add them, find the directions to solve a problem. In chapter 7, we can use the techniques which we'll learn later on, chapter 7, work, energy concepts, and we can solve most of the questions we did before. A new approach, a different approach. You use the approach of energy concept to solve a problem. It's much easier because energy is not a vector. It's a scalar, it doesn't have direction. So it's easy to add energies, normal. But it's not easy to add forces, vectors. So you can always think of solving whatever you've solved before using the concept of energy here, chapter 7, which means you have the freedom now. From now on, you have the freedom. You can use any technique you want, energy technique or forces technique, Newton's law. So today we'll talk about work and energy, chapter 7. Now, the first question is, what is work and how you do work? Work, let's call it W, right? The word work in physics is a little bit different from the word work which you use normally. Now, what do you need to do work? What do you need? You need? If I want to do work, okay, you need energy. But how do you use it? What do you need practically? If I want to do work on something, what I have to do? Applied force, yeah? So you need a force. So in work, you need a force. This is the first element, force. Okay? What else do I need? Is force enough to do work? No, like, this is the example. If I push the wall here, I'm applying a force. I have force. Am I doing work? Why not I'm not doing work? So you think that you need a movement, yeah? Displacement you need, not movement. You have to displace the object. If you don't displace it, then you haven't done work in physics. Okay, you feel tired pushing the wall. That's because you are doing internal work inside your body. Your muscles are stretching and you have stretching of the muscles will make you tired. Like when you carry something, okay? Internally, you have work. But externally, on the wall, no, okay? So what else do I need? Displacement. Force and displacement are the 2 elements of work. Without those 2, no work done in physics. Now, thinking of it, what we said so far, to be able to do work, what do you need? Someone said something here. What do you need?
Energy.
Energy. So if you don't have energy, you cannot apply forces, yeah? Now, let's say I have a chair here. This is a chair. And I apply a force. I push it. What happens? I displace the chair from this position to this position. So I have force and displacement. So did I do work?
Yeah.
Okay. Now, why I was able to do work? because I am alive. If I'm dead, I cannot, yeah? Which means I have energy. And what did I do with this energy? I transferred my energy to the chair. Through what? Force. This is how I translated the work. So work comes from transfer of energy. So if you want to define work, what is work? Transfer of energy to or from an object. So when there is a transfer of energy, what we say, a work has been done, yeah? So work is energy. I can say the word work is equivalent to the word energy. Because what is work? Transfer of energy. So you need a force and displacement to do work. Now, this is the concept here. Now, mathematically, how do I calculate the amount of work? Of course, I need force and displacement. So let's say we have an object, a mass. And you apply the force. Could be, this is one of the forces you apply at this angle. Now this object, initially it's here. Initially it's here. Now let's say finally it's there. So when I apply the force, the object moves from this position to this position. So from here to there, what is the displacement?
Delta x.
Or say delta r. You're thinking of x only. Let's say this is in space. So this is position number 1, r initial, r final. And this is delta r, and delta r is a vector. Okay? And force, vector as well. Now, if I put this object on a surface to make it a little bit clearer, so you have now normal force and Fg. Fg, normal force. Now the normal force and Fg, they are balanced, yeah? They have no effect on the motion on the x-axis. N equal? No, N here is not equal to Fg because F has component. So N plus F sine theta equal Fg. But anyway, these forces up, they cancel the forces down. But now we have a force this way, yeah? What makes the object goes from initial position to final position? Which force? Is it F? F is not in this direction. Component of x. So F cosine theta is the force which goes this way, yeah? This force is responsible for the motion, if there is no friction, of course. Now, we learned how to multiply vectors, if you remember, chapter 3, multiplication of vector. We said there are two types of multiplication, dot, cross. And the dot product means you have an answer which is a scalar. Cross product, another vector. Okay? And the meaning of dot product, it means if you have two vectors, vector A and vector B, and there is an angle between them, when you say A dot B, it means the magnitude of A multiplied by the shadow of B on A, yeah? And Bx is B cosine theta. So A dot B is A, B cosine theta. That's mathematically. Now let's come to here. For work, I need force and displacement. Force is a vector, displacement is a vector. Now look here, which way is the displacement this way, delta r, and F that way. So if I draw them here, I have delta r and F. And this is theta, same theta. If you multiply the force by the displacement, it gives you work. Now, as we said, this force not responsible for the displacement component. So the component means the shadow of F on, which is Fx, yeah? So now how many vectors do I have here? 2. Displacement and projection or shadow of F on x. Now if I multiply those two, that will give me the work done mathematically. So that's why we need dot product, because work, now we define it, work mathematically is equal to force vector dot displacement vector, dot product. So it's force dot displacement. Now, if it's a dot product, it means you can find it by the I of F by the I of delta R, J by J, K by K, but you add them without I, J, K, dot product, scalar. The other way which you can find dot is the magnitude of the force, magnitude of the displacement, cosine the angle between them. That's if you have the magnitude, and cosine the angle between them. Yeah? So now, if you want to calculate work, what do you need? Force and displacement. Now you have 2 ways to solve it. Either you use vectors, so force vector dot displacement vector, so you don't need an angle here. Yeah? Dot product, normal. The I by the I, J by the J, K by the K, but no I, J, K. Or if you have the magnitudes and the angle between them, then use this formula. So now we covered work as a concept, transfer of energy, formula. Now what's the unit of work? Newton multiplied by meter. And in Newton multiplied by meter is defined as joules. And remember, work is energy transfer, so it has the same unit of energy, joules. Joules. Right, what I'll do here now, I'll give you an example how to apply the formula. So you can write this example if you like. An object subjected to a force F equal 3I minus 2J plus K the object moves from minus 2I plus J minus 3K to I minus 5K position. A, find the work done by the force. B, what is the angle between the force vector and displacement vector? So an object subjected to a force, this is the force, and you could put the unit in Newton. The object moves from, this is a position in meters, to this position in meter. Okay? Find the work done by this force. Find the angle between the force and displacement vectors. This is what we want. Yes? All right, thank you. I don't. Right. Now, what do you need to find work? Force and displacement. What is this? This is position number 1, not displacement. This one. Or this is initial position and final position. Remember, for work, you don't need positions. You need change in position. So the first thing you have to do, you have to find the displacement. So what is displacement equal to? Delta R vector, final vector, minus initial vector. What is the final vector? Be careful. Final minus initial, not initial minus 1. I minus 5K minus, use parentheses, minus 2I plus J minus 3K. Now, if we subtract, remember, this will become plus. This is minus. This is a plus, yeah? I minus 5K plus 2I minus J plus 3K. Group the i's. 3I minus J minus 2K. Here we found the displacement vector. Okay? Now, if you have vectors, then what you have to do, dot product between the force and displacement. So work is force vector, displacement vector. Here, do I need to use magnitudes or vectors? Because they are ready, yeah? Which means now F, the I of F is 3. Yeah? The I of the delta R, 3. 3 by 3. I finish the I with I. The J, minus 2 by minus 1 plus 1 by minus 2. So we have 9 plus 2 minus 2 plus minus 2, 9 joules. This is the work done by this force to move the object from this position to this position. This is part A. Part B. What is the angle between the force and displacement? Remember the angle, it means, remember before I ask questions, giving you two vectors, I say, what's the angle between the two vectors? What did you do? Dot product, yes? But you already did part of the dot product, yeah? You did F dot delta R. So if we go back here, what is the other way for work? Force, displacement, cosine the angle between them. So what is the unknown here? Cosine the angle. Theta is unknown. So I have to know force, magnitude, displacement, and work. How do you find the work? We did it by dot product. So all what you have to do, find F and delta R magnitudes. So we say here, work equal force magnitude, displacement magnitude, cosine the angle between them. The work is 9 joules, yeah? So what is left now? The force magnitude. Force is a vector. How do you find the magnitude of the vector? Square root of the values. 3 square plus 2 square plus 1 square, yeah? This is F. Now delta R. 3 square. I need someone to calculate all that for me. minus plus 1 square plus 2 square. Multiply by cosine theta. So what is cosine theta equal to? 9 over the magnitude. Here you have 9, 10, 14, root of 14. And here 9, 10, root of 14 as well, yeah? So it's 14. So it's 9 over 14. And take the inverse. Theta is cosine inverse. 50. So the angle is 50 degrees between F and delta R. All right? So this is how we find work. Sometime by vectors, sometime by magnitudes. And of course you can find the angle between them as well. Right. Since work is energy transfer, we have to now deal with energy as well. But let's see what works do. If I go back to the example of the chair, if you have a chair or an object, a mass, and let's say I apply a force on the chair. Initially it's here. I apply a constant force. Finally, it's there, displacement. So I did work on the chair, yeah? Now, of course, the transfer of energy, it's here to the chair. I gave energy to the, so what happens to the chair? It was at rest, and then? Motion, yeah? So the energy transfer here is in type of motion, yeah? So like it made the chair move, speed up. Of course, you can take energy from the chair as well. Here I gave energy to the chair. How do I take energy from the chair? If the chair is already in motion, like it's coming towards me, I'll stop it. I'll try to stop it, yeah? So here the transfer of energy is from the chair to my body. I am taking the energy, okay? So I can give or take energy to or from, transfer of energy. So here we have something to do with motion here, yeah? Okay. Now, this course is about mechanics only. Of course, you have other courses. It's not just mechanics. Like physics 2, it's about electricity and magnetism. And of course, you have thermodynamics courses. So we have different branches of physics. But in all these branches, or chemical, some of you are doing chemical engineering, we always deal with energies, yeah? Like in chemistry, you have chemical energy. Mechanics, mechanical energy. Electricity and magnetism, electrical energy. We have different types of energy. But let's look at our course, which is mechanics only. So in mechanical system, we have a mechanical energy. Energy to do with mechanical system. Now, in mechanical system, we have two types of energies. Mechanical energy has two kinds. The first type of mechanical energy is to do with motion. So we call it kinetic energy. This is energy to do with, like the chair. When I pushed it, transfer of energy here shows as motion. So kinetic energy to do with motion. The second type of mechanical energy is nothing to do with motion. We'll come back to the second one. So I just put the title and just one word, and later on we go in details. It's called potential energy. Potential energy. Okay. Potential energy is nothing to do with motion. It's energy to do with the position of an object relative to another object. And usually an object with a planet, like the pen with the Earth, with the ground, yeah? Or the moon with Earth, yeah? Objects, masses, between masses, yeah? And this is an energy, nothing to do with motion, just to do with the positions and arrangement of object. As I said, we'll come back to it in details. I just say this is potential energy to do with position, huh? Relative to an object. So let's concentrate on kinetic energy for the time being. What is kinetic energy? It's energy to do with motion, okay? Whenever you have an object that in motion, that object has kinetic energy. Otherwise, it doesn't move. Now, how much is the kinetic energy? How do I calculate it? Let's start with the formula, and then I try to verify the formula. Where did it come from? So if you talk about kinetic energy, we give it the symbol capital K sub E. Kinetic energy. And kinetic energy equation is defined as half multiplied by the mass of the object multiplied by the speed square, or velocity vector square becomes scalar. This is how you calculate kinetic energy. Of course, the normal question is, where did this one came from, yeah? It's not like just suddenly we discover this half mv square. We have a reason for it. So let's see where this one came from. Let's go back to the example of the chair. Let me draw it here. But this time, I just draw it as a block here. There's a block here, a mass, on the floor. And there is a force, F, at an angle theta. The object initially here. Then it moves to there. Finally. Now, initial position, final position. So between those two, what do I have? Displacement, delta R. And of course, this will happen in a time, delta T. And when the object moves from, and here, let's say initially, it wasn't at rest. The object was in motion already, and then I apply the force. So what we have here? Initial velocity. And here, final velocity. Does this remind you of things we did in chapter 2 or not? Yes. Initial velocity, final velocity, displacement, time. What is missing? Acceleration. As well. So this object will accelerate because there's a change in velocity from 1 to 2. Right. Of course, I drew just one force, but there are other forces like Fg, normal, maybe there's friction, another applied force, just this for simplicity. If I use the equations of motion on this object, one of the equations of motion is this. Final velocity square equal initial velocity square plus twice acceleration delta what? R. Here I'm talking about an object moving in more than one dimension, yeah? 3 dimension in space, general case, and then we take it specifically here. Vector acceleration, displacement, vector. Of course, initial velocity is a vector. When we square it, it becomes a scalar, dot product, and here as well, scalar. And remember, this is a dot product, yeah? We agreed on that before, dot product. Now, this is chapter 2, motion, or chapter 4, sorry, motion in space. Now, chapter 5 is about Newton's law. Newton's second law, which says the total force, F net, equal ma, vector, yeah? So now, here, do I have acceleration? Yes. And in Newton's law, I have acceleration. So what is the acceleration equal to? F net over m. So can I substitute this one here? All right. So what we'll have? Final square plus 2 F net vector over m dot delta r. Now, let's rearrange the equation. Put the velocities on one side. So we'll have v final square minus v initial square equal 2 over m. I shift this one to the side, F net dot delta r. Multiply this side by m and divide by 2. So we'll have m over 2 final initial F net dot delta r. Open this bracket or parenthesis. So you'll have half m v final square. Half m v final square minus half m v initial square equal F net dot delta r. Right. Now look at the last equation. Equation has two sides, yeah? And they are equal in magnitude and equal in their characteristics, properties, yeah? What is this side? Work. And what is work? Energy transfer, yeah? So this side is an energy as well. So what this side must be? Energy as well. But this side, the energy is being used in form of force, yes? And this side, do I have force? What do I have? So what type of energy is this? To do with motion. What shall I call it? This is how it started. They said, okay, let's call this kinetic energy, because we know this side is energy and this side is energy. So this is something in you. What shall I call it? Energy. Kinetic energy. Now here you can see those are the same, yeah? This is final, this is initial. So it means this is kinetic final, kinetic initial. So this will be kinetic energy final minus kinetic energy initial equal. Okay, here be careful. It's not equal to work. It's equal to which work? Of which force? Total. Total force. So total work. So at the end of the day, I have an equation, a new equation, saying that K final minus K initial, it means the change in kinetic energy. So I can write it as delta K, change in kinetic energy, equal to W what? Net. Very good. This equation, it's very important in chapter 7. This is the central equation, the focus of the chapter. You always use it, always have it in mind. What does this equation tell you? It tells you in any mechanical system, whenever you calculate the total work on the system, it's always equal to the change in kinetic energy of the system. Whenever you calculate the total work on any system, this is always equal to the change in kinetic energy of the system, or the opposite. Look this way. Each time there is a change in kinetic energy of any system, this is equal to the total work done on the system. Don't get this one wrong. Delta K is not equal to W. Total W. Work total. Okay? W net. So now I found a new equation. And this is called the work kinetic energy theorem. It's the theorem that says that total work is equal to change in kinetic energy. So now I convinced you that why kinetic energy is half m v squared, starting from there. Equation. Now, work, vector or scalar? Scalar, because dot product, scalar. So can I add works? Yeah. So if I have work number 1, work number 2, work number 3, what's the total work? Add them. Yeah. But if I have forces? No. Vectors. So now you can see how easy it is to deal with forces but using works. Mm-hmm. So now we learn a second method of finding W net, because this is the first method. How do you find W net? You have to know what's the change in kinetic. And how you know how much is the change in kinetic energy? Go back and find the half m v squared final minus half m initial. The second method of finding W net, not by knowing the delta K. Let's say I have an object and I apply forces on it. F1, F2, okay, F3. This is at an angle alpha, this is angle gamma. Now, when you apply these forces, what happens to the mass? Either it doesn't move, if it was stationary, or it starts moving. And when it starts moving, it means there's an acceleration, yeah? So it moves with an acceleration. So let's say it starts moving, yeah? So initially it's here. And which way it moves? In the direction of the F net. So you have to know which way is F net. But let's say it moves this way, horizontally, just to make it easy. Let's say it moves here. So this is the final. So this is the displacement. How much is the total work on the system? What do you need to do? You have to say W net comes from the W of force number 1 only. How much work is done by F1? Plus W force number 2, work done by F2, plus work done by, add those 3, it gives you W net. So if you are looking for W net, and most of the time you need W net, total work, you have 2 ways, either changing kinetic energy of the system or the individual works of each force. Add them. Huh? So now I'll give you an example how to use this one. W net equal to that. Let me list what we did so far here as equation, so you know the summary of what we did. What we did so far, we said the work of a force can be found by force dot displacement vectors, or work of a force can be found by the force magnitude, displacement magnitude, cosine the angle between them. And what else? We learned that kinetic energy equal half mv squared, and the change in kinetic energy is always equal to W net. Yeah? And what else? Just now, W net equal work of the first force plus work of the second force plus work of the third force, and so on. It depends on how many forces you have in the question, the individual work. So I want to apply the last equation. W net is the summation of all the works in the question. So write this example with me, maybe example. A mass of 3 kilograms subjected to two forces, F1 60 Newton at alpha 30 degrees and F2 40 Newton at gamma 20 degrees as shown below. The surface has a coefficient of kinetic friction of 0.3. 0.3, and the mass moves a distance of 10 meters. So a mass of 3 kilograms subjected to two forces, F1 at this angle, F2 at this angle, as shown below. I'll draw the surface has a coefficient of kinetic friction of 0.3, mu. And the mass moves a distance of 10 meters. Now, this is the first question. A, find or calculate the total work done on the mass. B, if the mass is initially at rest and gains a speed of 2 meters per second at the end of the distance, what is the speed at the end? So find the total work done on the mass, part A. Part B, if the mass is initially at rest and gains a speed of 2 meters per second at the end of the distance, when it moves to the end, what is the speed at that end? Final speed. This is the diagram. The mass is here. We have F1 this way, and the angle alpha, 30 degrees. And here we have F2, and the angle gamma here, 20 degrees. Of course, F1 is 60, F2 40, and we have friction, and the object moves from initial position here to final position there. And from here to there is 10 meters. Right. The object, it's on a horizontal surface. And there is a friction as well, because I have coefficients of friction. Now, what's the question, the first question? What is the total work done by all the forces on the mass? To find total work, what do you need? If you're talking about this one, you can find W net by knowing the change in kinetic energy between initial and you don't have information. At rest, and the final velocity is unknown, or speed. So what you have to do, you have to go this way. W net, you have to know work of force number 1, plus work of force number 2, plus work of force number 3, 4, 5. It depends on how many forces we have. Now, let's see here on the diagram. How many forces do we have on the diagram? No. 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 5. Major forces, not component. F1, 1. F2, 2. You have Fg and N and a friction. Okay, how many now? 5. So it means I have to do 5 works. Add them, it gives me total work done on the system. Right, let's do them one by one. First, WF1 only. What do you need to find W? You need the force, displacement, and cosine the angle between them. That's when you do, of course, here you don't use vectors because on the surface, use magnitudes. And you don't need the components. When you do work, you don't have to put the components. You can, it helps you, but there is no need. You need the original force. So here, what do I have? Force 1 magnitude, displacement magnitude, cosine the angle between them. Now, where is F1? This way. Where is displacement? This way. What's the angle between them? 30. I'll do a sketch here. This is initial, the start of the tail, and this is the final. This is delta R. And here you have F1. So this is the angle between them. Is it alpha or not? Yes? This is delta R. Start from here, finish there. And this is F1. So the angle is the same. Horizon. So what you put here? Cosine what? Alpha. Now let's substitute. What is F1? 60. Delta R. Cosine. Okay. You can do it now and you find how many joules. This is W F1. Now you move to W. Yeah, 500. Let's say around 520. Joule. That's F1. Now we do F2. Work of F2, not F2, work of F2. F2, magnitude, displacement magnitude, cosine the angle between them. Yes? What is the angle between F2 and displacement? 180. It's not a 20. Then this, it's not a 20. The angle between delta R this way, and F2 this way. So if I want to sketch it here, it's like that. This is delta R, and F2 is this way. And remember, you know this is 20. So the angle you need is this. This is nothing to do with polar angle. Don't mix up this with what you land. I want the angle between two vectors. How you find them is up to you. But it's not like you go positive x anti-clockwise. No, here it just looks like the same, yeah? So you need the angle between the F and delta R. So this is the angle. How much is the angle? 160. 160. This is where you have to pay attention when you calculate work. You need the angle between two vectors. You don't need the directions. You don't need the polar. Just see how you find the angle between two vectors. So the angle here is 160. So what is F2? 40 by 10 by cosine 160. So this is WF2. How much is it? 200 exactly? 200. Definitely is minus. Why? Because the angle is more than 90, and cosine of an angle more than 90 is always negative. Second quadrant. Minus. Minus what? 375.8 joule. This is the second work. Now let's take the third work. Where does it come from? From which force? I have Fg, and I have normal, and I have friction. Now, why did I put friction this way? I didn't put it in that way. Who told you? I didn't say it moving. Oh, you find this one 10, yeah? Okay, I could have drawn this one.
We assumed that it's this.
No, you can tell from the values. This is 60, 30. This is much bigger than 40. So the possibility this component, this side, is bigger than this component. Look, this one, it has F1 cosine alpha, and this one has F2 cosine gamma. If you calculate those, you find this side is bigger than this side, so it moves that way. But regardless, a friction, always opposite motion. Opposite motion. So you don't have to worry, just put it opposite the motion. Right, so now let's go to work number 3. Huh? So W, which W? W of what? Let's take W N, normal force. Normal force. Which means I need the normal force, magnitude, displacement magnitude, cosine, the angle between them. Which way is N? Up. Which way is delta R? Horizontal. What's the angle? Okay, I put a sketch here. This is N, and this is delta R. So this is 90. Now cosine 90? 0. 0 multiplied by anything, 0. So how much is the work done by normal force? Okay, this is always true. From now on, don't calculate the work done by normal force, because normal force always makes 90 degrees with the motion. So there is no point of calculating the work of normal force. The next force, Fg. W Fg. So what do I need? The magnitude of Fg, magnitude of displacement, cosine the angle between them. What's the angle, Rand? Between Fg and delta R. 90 as well. Anyone think it's 270?
I did.
You did, yeah? Why you think it's 270? Because you're thinking of directions. Here you don't need direction. You don't have to measure positive x. You need the angle between two vectors. This is vector number 1. And this is vector number 2. What's the angle between them? Okay, 90. 270 is not wrong. It gives you the same answer. But as a concept, it's wrong. You are looking for something else. We need the angle between them. So if I want to draw it, Fg is this way. Delta R is this way. So the angle is 90. Again, it's... So the work of gravity is what? 0. Now, I know some of you will conclude this, that work of gravity is always 0. Yes? Wrong. Here is 0. But work of normal force is always 0. That's the right conclusion. But WFG is not always. Of course, I'll give you some examples that when FG work is not 0. I'll come to it. So just remember, this is not always true. What is left? FR, work of friction. So we need WFR. So FR magnitude, displacement magnitude, cosine the angle between them. What's the angle between delta R and the friction force? Always or sometime? Because the object moves this way, friction, opposite. Moves this way, friction, moves this way, friction, opposite. So it's a rule. The angle in friction work is always 180. So here we have 100, and I'll draw it for you here. You have delta R going this way, but the friction opposite, so it's 180 degrees. FR, to find it, what do you need? Mu normal delta R. Cosine 180 minus 1. Mu in the question was given, yeah? How much was the mu? 0.3. What is left? N. What is N equal to? What is N equal to? Okay, that's the trap. You've fallen to the trap of making one of the common mistakes. These forces, they have component up. N is not equal to Fg. Not always. There's no such a rule. N is always equal to Fg. Here I have three forces up. N is the reaction of the surface, and two components from F1 and, okay? You can see deliberately I didn't put the free body diagram to catch you on this. So you remember that this is one of the mistakes. So here you have F1 sine alpha, symbolically, and this is N, and here you have F2 sine gamma. Those three. Okay, now on the side, calculate that, because you have to put N, yeah? So what we have to do, if I do it here, you say N plus F1 sine alpha plus F2 sine gamma equal to Fg. So on the side, find what is N equal to, value, because you have all the values, including the mass. So one of you can calculate N, and then put N here. Multiply by mu. Can you do it? So we can find W net. So W net now equal WF1 plus WF2 plus WF plus WFR plus WN plus WFG. These are all the forces. Now these two are zeros in the question. So what is left? WF1, WF2, W friction equal W net. Got the value of N? N equal, if I write it here for you, N equal Fg minus F1 sine alpha minus F2 sine gamma.
It's minus 14.
You can't have it minus. N cannot be minus. Unless I chose, okay, this happens. If you choose a question with the wrong values, you know what happens here? These forces are so high, they lift the object up. So it's not on the surface. It's the wrong, I have the wrong numerical values in the question. Possible, yeah? But just imagine that, think of it symbolically here. Ignore the values. Ignore the values now. You can, no problem. Change the mass. Make it so heavy. Good point. So change the mass in the question to something heavy, yeah? So heavy. It was a 3, yes?
Yeah.
Make it 20.
I just did it 20.
Yeah, make it 20 kilo.
152.5.
So now it's okay, not minus, yeah?
It's plus.
So change the question, the mass to 20. Because I didn't check the values, so sometimes the values of these forces are much higher than, then you have no friction, okay? And you are lifting the object. Anyway, so now what is N? 152. Okay, now find now mu N, delta R. So now the work of friction, mu is 0.3, N 152.5. Delta R is 10 meters, multiplied by -1. So it's minus something.
It's minus 457.5.
400 point? 0.5. 457. This is joules, yeah? The work of friction. Okay, what you do now? Just substitute here. So what is WF1? 520 joules. Plus WF2 is a negative one, yeah?
Minus 37.
Okay, so I put it minus here. Minus 37.
5.8.
And friction? Minus.
457.5.
And this will give you the total work done, yeah? It will be negative. Minus 331 joule. This is W net.
It's minus 520.
520 minus 371. Anyway, remember, this question is not for values. I don't want just how you do the angles, yeah? The rest is just, ignore the numbers, just see the procedure. The procedure is that find the individual works, and when you find the individual works, just be careful of the angle. Once you have all the works, add them. It gives you W net. All right, this is the second way of finding W net. What was the part B question? What is the final speed, yeah? Yes. Okay. If you know W net, it means you know delta K now. So part B, you say kinetic final minus kinetic initial equal W net. Kinetic final, half mv square final minus kinetic initial, half mv initial, and W net is what you found. Now, all what you have to do, this is of course 0, because it started from rest, yeah? All right? But I have a problem here. Still, we have a problem of numbers. You see the problem? If I put minus here, I'll have v square equal negative. And that's impossible, which means still the values given are not right, yeah? Okay? So we leave the example as it is, but do it not numerically, symbolically, the steps. The steps are these. Add the force, add the works, find the total work, and the total work is change in kinetic energy, yeah? That's it, yeah? So now this is the second way, finding W net. And then use W net, change in kinetic energy.
The question, you're going to continue or it's done?
Oh, this I finished.
Okay, in the question it said gain the speed of 2 meters per second at the end of the distance. What is the speed at the end?
Which means it's the wrong question. I have to ask what was initially then. And then it works maybe. It works. I gave you the final, yeah?
Yes.
So then I have minus with minus cancels, yeah.
So you want
Good.
the initial speed.
Okay, yeah. So here it's the opposite. Thank you. No. So we have half mv square initial equal w net. Now this time this is 0.
No, this is
This is none.
the V is 2. The final is
2. Oh, but still, let's see if it works. Because the values will half the mass 20 we said, yeah? And this is 2 square minus half 20 V initial square, and this is minus 3.1.2. I should have checked the numbers before, because I did it in a haste. I just was putting any numbers. It's the idea how you do it anyway. So now this is, will it give you a positive value? You can calculate it. This is 4 over 2. This is 40. And this is 10 minus 331.2. Okay, so it's still, yeah, this is minus 3312 minus 40 minus 10. Yeah, I think now it gives you positive because this is still negative. And you find V1. Yeah, because this will be negative. Negative cancels, yeah? And divide by 10, yeah?
The question you said it was at rest and then...
You have to change it. Like, it's not at rest. Remove the rest. You just have the final velocity. As I said, the idea is that how you do it, the procedure, not the numbers. The numbers can be changed. So all what we have to do, we have to choose the proper numbers to give you a proper answer. Right. So this is how you do W net.
It's 1.1.
It doesn't matter. Now we have to ignore all the numerical values because the question, just look at the procedure. Right. Now what we did so far, we talked about work done by a constant force. The force you apply, it's either 10, 20, 30 newtons, doesn't change. Now what if you have a variable force? How do you calculate work? So the next title is work done by a variable force. When there is a variable force applied to an object, how do you calculate the work done by this force? First, don't make the mistake of saying that W equal to F dot delta R or W equal F delta R cosine theta. When do you use this formula? When the force is constant. One value. But if this force is variable, it's a function. Like here, the force is a function. It could be a function of R here. And here, function of R or X or Y. Variable force. Let's say you have a force, and the force is a function of R, or the force is a function of X, function of Y, function of Z. Changes with position. Of course, when the force changes, it changes with time, yeah? But we don't want to include time here. We need displacement. So instead of saying changes with time, it changes with position. That's important, yeah? So you have a force changes with position. Let's take an example and see what we do. But before the example, I just give you the formula. If you want to calculate the work done by a variable force, it's easy. Just do integration. Integrate the force. So W for a variable force, let's say F of R, variable. Look, the force is a variable one. It's integration of the force function dr from initial position to the final position. This is for a variable force. Work done by a variable force. Now, example, let's say an object is subjected to a force F equal 3x squared minus 2x. And it moves from x equal 1 meter to x equal 3 meter position. Find the work done by the force. What's the work done by this force? So an object subjected to a force, look at the force, constant or variable? It's a function. So if the force is a function, how do you calculate the work? Integrate. So now, if I want to do the work here of this force, of course this force is a function of x, on x only. Doesn't matter. So W f of x is integration of f of x, not dr, because you are on x, so dx. From x1 to x2. Initial to final. Now substitute. What is f of x? 3 minus 2x. This is the function, dx. And I have to integrate from position number 1 to position number 3. Now, what's the integration of this? 3x cubed over 3 minus 2x over 2, and the limits from 1 to 3. 3 with the 3, 2 with 2. So we have x cubed minus x squared from 1 to 3. Now, how do you evaluate? Remember in calculus, upper first. Upper minus lower. Don't make it the other way around. So here we say 3 cubed minus 3 squared. This is the upper. Minus, bracket, the lower. 1 cubed minus 1 squared. This is 27 and 9 here, yeah? Minus, this is 1 minus 1, 0. So the answer is 18 Joule. Yeah? Now, you got the idea of variable force?
Yes.
Whenever you have a variable force, what do you do? Integrate the function. And the limit is from first position to final. And say upper minus lower. Now, when the force is variable, not necessarily you have the equations. Sometimes we give you a variable force, but graphically. So if you have a graph, how do you find the work done? What is the other meaning of integration? Under the graph. Graph of what? Force versus position. So if I have a question saying that there is a force applied on an object, this is x is the position in meter, and this is the force. And 0, and the force behaves like this. What do you see here? A constant force or a variable force? Variable. Now the question is, how much is the work done by this force? Like from 0 maybe to, well, I don't know. I don't know if the scale will work because I don't want to make the same mistake of giving you a value, it doesn't work. So I have to know what are the values. Let's say from here to there. What is the work done? Area. If you want the total area, 1, 2, 3. Of course, this area, either you're thinking of it as a trapezoid or you can divide it to 2. So what we say here, work equal area under the graph of force versus position. So how many ways do you have to find the work done by a variable force? Two. First, if you have equation of force, integrate the force. Second, if you have a graph of force position, find the area under the graph. Remember, when you say area under the graph, sometimes the area is negative. And work could be negative. Or here, positive. Leave it. Don't use absolute value. Because sometimes you give energy, sometimes you take. By the way, when we say the work is negative, what does that mean? And when we say it's positive, it doesn't mean right and left, because it's not a vector. It means increase or gain, loss. Gain and loss. Huh? You give energy or you take energy. So plus and minus allowed in work, energy, but doesn't mean direction. Positive and negative. I think up to now, you have now enough information to start on the review problems. You can do at least 10 questions of the review. Practice on them tonight, maybe tomorrow, before it's too late. Remember, not much left for the end of the course, and we'll go faster. Okay, and we have exam next time. But the exam will be 1 hour. So the first half an hour I'll teach, and then, so we'll do half an hour. And thank you. Hi. We are still in chapter 7, work and energy. And today I'll just talk about work done by gravity force. And then after that, I'll talk about work done by a variable force and a special case of that. If you remember, if you want to find work done by any force, you need the force, the displacement, and cosine the angle between the force and displacement. So here I'll draw different cases, and we see how to find the work done by gravity force only, not other forces. So first, you might have the object on a flat surface. So Fg is this way. Of course, we have other forces, but I'm concerned about Fg only. And let's say it's moving this way. So the displacement is this way. So what is the work done by gravity force here? Fg, displacement, cosine the angle between the displacement and Fg. How much is it? 90. Cosine 90, 0. So there is no work done by gravity force if the object moves on a flat surface. Yes, this is case number 1. Case number 2, if the object moves on an inclined surface, theta. Now here you have 2 cases. When the object is going up or when the object is coming. Now let's take the first case. Let's say initially the object is here, initial position on the incline, and it's moving up to a final position, F. So which way is the displacement? Upward, this way. I can call it delta R, you can call it X, D, doesn't matter, I stick to delta R. Now where is Fg here? Perpendicular on the ground, yeah? Here as well, perpendicular on the ground. And this is the direction of delta R. So now if I want to find work done by gravity when it's going up, WFG, I need Fg, delta R, cosine the angle. Okay, look here on the board. Is theta the angle between the displacement and Fg? No. Theta is not the angle. Theta is the angle of the surface. So where is the angle I'm looking for? Is this angle. This one. Let's say alpha. So is alpha here 90 or more than 90? Okay, so it's more than 90. So you have a value for it, yeah? Now, more than 90 by how much? By theta value. So this alpha is 90 plus theta. 90 plus theta. So here alpha is 90 plus theta, the angle of the surface.
Doctor, why isn't it 180 minus theta?
180?
Yes. So this is the x, right?
This is the x-axis. This angle is more than 90. Calculate it because you have, this is FG, not FG cosine. Okay, you got it? So when the object is going up the incline, the angle is more than 90. 90 plus theta. Which means the work of the gravity is positive or negative? Negative. More than 90 cosine an angle in the second quadrant. So the work of gravity when it's going up is negative. Of course, you're going against gravity. You're going up. Now, the second case, when it's coming down. Theta. Initially, it's here. Finally, it's here. So it's delta R is this way. And FG down. Delta R. So where is the angle between FG and delta R? It's this angle. Gamma. How much is gamma? 90 minus. It's less than 90. By how much? By theta value. So here we say WFG equal FG delta R cosine gamma. And gamma is 90 minus theta of the surface. That's it. So these are the cases, yeah? It's not always like zero work of gravity, up incline, down incline on the surface. Now, the next thing is how to find the work done by a variable force. Work done by a variable force. I think we talked about how to find, but now we take a special case of that. Work done by a variable force. If you have a variable force, how do you find work? Work of a variable force, F of R, is integration of the force dr from initial position to final position, integration. And if it's a graph, like XF graph, we say the area under the graph is W. Work is area under the graph of F versus X here. So whenever you have a variable force, you have to integrate the function, if you have the function, or you find the area under the graph. Now, we have a variable force example. We'll talk about it now. Work done by a spring force. Here we have a case of what we call Hooke's law. Hooke's law. So this is an example of a variable force. Hooke's law. Some of you done an experiment on Hooke's law in the lab. But now we'll go to the theory of it. Now, let's say you have a spring. And when we say spring, we mean something elastic. Spring or a rubber band, same, elastic. Not a plastic, something which you can pull to an extent. And then if you remove your hand or the force, it comes back to its original dimension. So if I have a spring, I put it horizontally on a surface, and here it's connected to a point. Now, initially, the spring is not stretched or compressed. So this is the initial position, xi. When it's not compressed or stretched, we call this point equilibrium position. Equilibrium Equilibrium position means the spring is not stretched or compressed. Now, if you apply an external force, your hand, Fa, what happens? Spring will extend up to a point and stops, yes? That's when you apply a constant force. You don't change your mind while you pull. You start from the beginning, you say, I want 20 Newton, just 20 Newton, or 10 Newton. So when you apply the force, the spring will extend to a new position, X final. Still you have Fa here. There. And from X initial to X final, what do we have? Displacement. Delta X, displacement. Now, we have a force. So do we have work done or not? Yeah. By this force. How do you calculate the work done by this force? This force is constant or variable? Constant. So to find the work done by Fa is easy. WFA is the force magnitude, displacement of the spring, cosine the angle between them. Tell me, what's the angle between them? 0. Always. When you pull a spring or when you compress it, your force makes a 0 degree with the extension or the compression. Always. Constant. This is the work done by the applied force. Now, when you pull a spring, what do you feel? There is a force resisting your pulling or not? Okay? Which way is this force? Towards the spring. This force comes from the spring itself. In this case, when you pull, the spring pulls your hand. We call it F sub S, spring force. Force of the spring, Fs. Spring force, yeah? It's a real force. It's inside the spring. That's where when you pull, you feel that you have to apply a force. Otherwise, it doesn't extend. Compression as well. This force, Fs, if you want to know if it's variable or constant, remember, when you pull the spring to 1 centimeter, you feel it's easy or hard in the beginning? Easy. But the more you extend it, the harder it gets, yeah? Which means the force of the spring is constant or changing? Variable force. So Fs is an example of a variable force. The spring force is always variable. Depending on what? On the position. So if at this point, Fs has a value different from another extension, or compression, same. So Hawkes, the scientist Hawkes, studied this phenomena, and he found that the spring force is directly proportional to the displacement of the spring. The bigger the extension, the higher is the spring force. That's what he found. So to create equation, you need a constant. But before that, delta x is a displacement, which means x final minus x initial. Now, if I take x initial to be the equilibrium position, 0, yeah? Not compressed, not stretched. By the way, this side is positive. Extension. This side? Negative x. So I can replace delta x by x, because xi? 0. So Fs directly proportional to x. But which x does this mean? X, the final position, or the extension. There is no need to put delta x, that's x. Remove the proportionality, you need a constant. The constant, we call it kappa, not k, kappa, with a loop. Kappa x. So kappa is a constant. This is Hooke's law. Fs, force of spring, equal kappa, constant, x. Kappa, we call it the spring constant. Or the stiffness. How stiff is the spring? Yeah? Stiffness constant or spring constant kappa. Now, before we go further, now we have to discuss this equation mathematically. X means delta x, and delta x means displacement. Displacement is a vector or a scalar? Vector. So this side is a vector or scalar? Vector, constant scalar. This side force, vector. So now vector equal vector, yes? This equation tells you this vector equal to? Vector equal vector. It means that the two vectors are equal in everything, equal in magnitude and direction. Now, is this true here? Which way is Fs here? This way. Delta x? Opposite, yes? Always or sometime? Now, if I compress spring, which way is Fs? Out. Which way is delta x? Opposite. Which means those two vectors, they always? So this equation is not right. Need a minus. So in Hooke's law, we have a minus. This minus means the two vectors are opposite each other, always, yeah? That's the meaning of minus. But you don't need it in calculation because you deal with magnitudes. Okay? This is the one you need to deal with it as vectors. Now, kappa, how do we find kappa? Fs over? And what's the unit? Per meter. The unit of kappa is in Newton per meter. Be careful with kappa because we have capital K is kinetic energy. This is kappa. Put a loop so you remember this is a spring constant, not a kinetic energy. So easy to get confused between those two. Right, let's discuss kappa. Let's say I have a spring, and the kappa of the spring is 10, what, Newton per? What does it mean, a kappa 10 Newton per meter? It means you need 10 Newton to extend this type of springs by 1 meter. 10 Newton to extend it by 1 meter. This is 1 meter, yeah? Now, this spring, which has this kappa, it's a soft spring or a hard spring? Why hard? 10 Newton. Enough to extend it by 1 meter. Soft? Kappa is low. Yeah? Do you know how much is 10 Newton? Think of if I use the spring vertically, not horizontally. This is initial. If I put a weight here, Fg, yeah? When Fg is 10 Newton, what does that mean? What's the mass? Nearly 1 kilogram, yeah? So 1 kilogram, if you hang 1 kilogram here, it extends the spring by 1 meter. So soft, yeah? Kappa is low. But if you have a kappa of 1,000, hard. Okay? Now in designs, now you see this in your designs, in civil engineering as example, we use springs, yeah? Nowadays they use, similar to springs, they have rubber. They put it underneath the buildings to absorb the shock from an earthquake. Yeah? So instead of the building taking the shock, start vibrating, going up and down or in shear wave, start moving sideways, what happens? The energy comes to the rubber or the spring. The spring will be compressed, so it takes the energy, and then it releases this energy not in one go. Probably 1, 2, 3, and stops, yes? So if you have 100 joules coming, what are you doing? You're dividing this 100 to 3 stages. 33, 33, 33. So it's this way, you don't damage the building. So one of the applications of Hooke's law in civil engineering, yeah? Or architects, you do it as well. Other applications of springs and chemical engineering. The spring is the model for the vibrations of atoms. So if I have an atom here, or a molecule, it's surrounded by others, yeah? 3 dimensions. You have one that way. So you have many. So when the atoms vibrate, we imagine this, that this atom and this atom are connected through a spring. So what you do here, you say that the vibration here comes from the springs. So when this atom moves to this side, what does it do to the spring? Compress it. Which means now the spring has energy stored in it. This one will extend. The other one compress, stretch, yeah? And then you transfer the energy from here. Now if you heat up the object, you're giving energy, yes? Where does it go? To the springs. So start vibrating, yeah? And you transfer the liquid to gas. But if you take the heat, take the energy from the springs, goes back to liquid, yeah? But of course we don't have springs in atoms, yeah? We imagine that. So how much energy do we have here? You need a model. Your model is based on Hooke's law. Not exactly the same, but similar. So if you know the force of the springs, constant of the spring, then you can apply Hooke's law. Not as simple as that, but this is the start. This is the basics. So this is an application in chemical engineering. You have many applications. Physics is based on Hooke's law, modern physics, because it's a model for energy in solids. Now, what is next? What we need now? Remember the title says, work done by work. What did I do here? I just found the force of the spring. Now, is this force constant or variable? So how do you find the work done by the spring force? You have to integrate the force. So now we'll integrate this force. And instead of Fr, what do we have here? F spring. So I have Fs dx, because I'm moving in x here. You can have dy if you're moving here. And instead of R1 and R2, I'll have x initial, x final of the spring. Now, Fs, what's the equation for Fs? Minus kappa x dx. Integration from x initial to x final. WFS. Now, what's the integration of minus kappa is constant outside. So you have to integrate x only. So you'll have minus kappa x square over 2. And the limits from x initial to, this is the work done by the spring force. Let me move this one. Now substitute upper minus lower. So the work of a spring, instead of Fs, I put S, work of spring. Same. I'll have minus half kappa x square final. Or maybe I confuse you with this one. Let me do it in stages for you. Minus kappa and 2, I put it outside. So upper minus lower, yeah? Upper minus lower. Now open the bracket. You'll have minus half kappa x final square minus minus plus half kappa x square initial. Work of the spring. Now, the first one is negative, the second term is? So it's better to swap them. Always have the positive first. So at the end, we say the work of a spring is half kappa x initial square minus half kappa x final square. We found the equation. What's this equation for? To calculate the work done by the spring force. Work done by the spring force. Okay? Now, So if you have a spring, how do you calculate the work done by a spring? What do you have to do? Don't integrate. Finished. This is your equation. All what you need is, what is the kappa for the spring? What was the initial position of the spring? What was that? And don't forget squares. By the way, this is not delta. Delta is final minus, initial minus final, and you have a square as well.
This is included in the formulas?
Yeah, it's included. Yeah, this is included. Work of spring. But just be careful. This is initial, this is final, not the other way around. So if I have a spring now, and I pull it with a force, yes? How many forces now I have?
2.
More than 2. You're thinking X only. Why?
4.
FG and normal. What else do we have? Maybe we have a friction. So I'll put all the forces. Maybe I have a friction as well. This is a general case. Not always you have the general case. Maybe you have a special case. Maybe you have a spring on a frictionless surface, so no friction. Or maybe you have a spring and moves on a rough, but there is no applied force possible. When you say no applied force, of course you say, how come it went? You pull it and then release. So there is no applied force. It goes by itself. So if I want to apply the kinetic energy work theorem of this chapter, which says W net always equal to change in kinetic energy. You remember this equation? The total work is always equal to the change in kinetic energy. I want to use this equation for the spring. This is the standard question. You have 10 or more questions about spring. So if you have a spring moving horizontally, the first thing is, this is your equation. Total work is change in kinetic energy. Now, how many works do we have in the spring? General, how many works? How many forces? 5. 2 of them, 0. No work of N, no work of AG. So what is left? 3 works. So W net is equal to W of the spring, W of the applied force, W of friction force, equal kinetic final minus kinetic initial. Now substitute. What is the work of spring? This equation, yeah? So we have half kappa x initial square minus half kappa x final square. Plus, how do you find the work of applied force? Force displacement cosine 0. Fa delta x of the spring cosine 0. Last one, work of friction. Plus Fr delta x cosine 180 equal kinetic final means half mv square final minus half mv square initial is the initial kinetic. This is your general equation for any spring, yeah? Read the question. If you have a friction, you keep this term, yes? If you don't have friction, out. If you have applied force, keep it. You don't have, out. But you can't say I don't have a spring because you have a spring. So this is the minimum. The minimum is Ws equal delta K. Maximum, all 3. Between either you have friction or applied force. Okay? Now what you have to add to this, how do you find Fr? Mu n. And what is n here equal to? Fg. So I change it. Mu mg. Right? What you need with this one, a small table. When you want to solve a question of spring, always ask yourself, what is the initial position of the spring, xi? What is the final position of the spring, xf? What is the initial velocity of the spring? What is the final velocity of the spring? This table is very important. Fill it. Now, what's the question here? Could be anything, yes? But the concept is one. This equation. I can ask you, what is the initial velocity of the spring? What is the final velocity? What is the mass of the spring? The mass attached to the spring. Displacement. Friction force. Coefficients of friction. Applied force, how much is it? Kappa of the spring. Initial position of the spring. Final position. Do you have to remember all these questions? No, just remember the equation, and then the question could be anything. The rest is math. Okay, so that's it, yeah? So this is where we'll stop now, and we continue next time I see you. Thank you.